Okay, folks, I thought I'd do this slideshow again. You'll find if you go back in my photo stream or my YouTube channel, actually, that I do this occasionally, right? It's it's a workout for me. So it's like when somebody does a ritual, like a tea ceremony or something, maybe. You practice your slides, you could say. And you're like, well, I just want to come to the finished thing. I don't want to watch you practice. And it's like, well, at this point, right? What's the difference? But I'll deliver it in a different way. Like my point when I do this each time is not to just parrot myself, right? So this is a picture taken by me. It's not off the internet. I did get to go here. And in my storytelling, it often links to things about Bucky's relationship to his other peers, his engineers, the Synergetics companies, the Dewline domes. There was almost a mass production aspect to it there with Don Richter and Temcor, and that's a whole generation of engineers that I would put between my time and Bucky's time. It's just he lived a long time, so T.C. Howard, for example, would come in as in that case. I'd also talk about some of the backlash against Bucky, right? How that could be. You can find the weak spots in a person's story, and it's all about mixing, right? Like sitting at a mixing board and pushing certain frequencies, right? So, what is our attitude towards the Bucky stuff? Now, Critical Path, D.W. Jacobs, the playwright who wrote that monologue for a Bucky character, very interesting, tightly choreographed style of play. He was on a Philadelphia channel recently talking about how he got introduced to Bucky, and the Critical Path book here was pretty important for him. He got sucked into that vortex. So this is my bookshelves. Another picture from that doesn't. It's not exactly like that today, but I do think. Did I bring Critical Path? Here's a paperback version. So like if you're giving this slideshow, don't forget show and tell. You can do it. If you got toys, I got my S module here in a jar, and my E modules. It's kind of a joke to concretize them like that, right? Because they're abstract platonic forms, but onward. So these books, the Synergetics in the middle there especially are, well, they're both there, the two volumes separated by Critical Path in two versions or two editions. They're very geometric, and the project here is kind of invent my own language and simultaneously translate whatever anyone says to me, see if my language can handle it. So he goes around the world listening to people and translating it into this emerging self invented language, which incorporates everything he thinks is very critical to his thinking. Like, here's a place to distill it. And he got a lot of encouragement from Ed Applewhite, who I'll show at the very end a picture of, to actually get it down to where we can distill it into a book for the ages, right? And not just have it kind of disappear with you. Like, Ed really did see value in what Fuller was saying, mathematically and otherwise. And so, but what were his credentials? And in other words, when you're striving to establish authenticity or credibility or whatever, get a foothold, a beachhead for a discipline, that's like building a sandcastle. What's the half-life? What's the staying power? Okay, so it's one thing to have two books out by Macmillan, actually multiple books out published, and to have awards and to have degrees, honorary degrees thrown at you, and to go around the world a lot of times. Like by all conventional standards, many patents, the dome assembly lines, he was a great success story, right? As an individual. The tendency, though, has been to write him off as, well, nice try, too bad, or something like that, which is ridiculous, right? Given objective measures of like, well, how many books did you write, if you're a journalist writing about what a failure Bucky was, isn't that a little two-faced, maybe? All right, not that all journalists should look up to Bucky, not like that, but have a little respect. So that was a slightly different take. Now here's the problem for people just to get into synergetics. His proposal here is to not really take the cube as seriously in terms of it's our foundational shape to understand first, second, third power. Instead, the tetrahedron, which is a simpler shape in terms of number of edges, number of faces, let's use that as our first, second, third power sort of conversation piece. And so he develops this easy to follow beginning of close packed spheres, which we do in the sciences anyway. Like, this is very familiar territory. It's like, well, okay, so Bucky's into sphere packing. You can run circles around synergetics in terms of jargon, in terms of, I like Barlow packing. I got that from Conway. Speaking of Conway, where I talked to him was in the math forum and various discussion groups. I put like 10 years of writing into that, and the discussion lists were taken down. We were warned NCTM was moving in, and now it looks like they may have crushed the whole website, mathforum.org. Check it out. Maybe it came back. They have a nice, we're closed for temporary maintenance, be right back kind of message, but I'm suspicious. But maybe they're not lying. Okay, so how can this tetrahedron serve as unit volume? Its edges are second root of 2, and we know that times itself is not going to be 3, but that's what we would need it to be if the tetrahedron inside were to be 1, which it is in our accounting method. Now it says the edge is 2, and 2 times 2 times 2 is 8, and that's true. The little, like, if we do this like a frequency thing and subdivide, we're going to get, bigger and bigger numbers if we keep increasing that 2. Like, there's a third power relationship there. But that's 2 radii, so we could call that 1 diameter, right? So that's the edge of 1 that we talk about with the prime vector. Goes from one closest packed sphere to the other, unit radius, as the spheres are unit radius. And so you started to get the idea of what we're doing here. We're modeling third power growth as on the far right, not as on the cube column. Right? These are 2 parallel columns showing what you could call second and third dimension or something like that. Area and volume, right? If you want to tangle up the term dimension right away, you can, or just talk area volume. And so here's the break, or the fork, the branch, where Fuller's going to just sort of distance himself from our commitment to 3-dimensional space, and then adding time, and then talking about space-time. He's not against the space-time mix. He's got time size going, which is very similar. That where we have size and relative size is also where we have time and relative time. Big things take longer to create. Big energy, little energy, right? Relative energy. That's what you'd call the world of frequency in the language of synergetics, or you could, right? And then he's going to take away our idea that in this world, right, in this semantic space, in this namespace, that we need dimensions like we do usually. Like, let's just start with the tetrahedron. Is 4-dimensional, and everything has bulk. Everything takes up volume. We just define it that way. I don't care how small your point is. It's there versus not, okay? It's a ray tracing world, you could say. And it's very definite, finite, very, just think of it as used in a niche discipline off to the side, like a ray tracing / art / movie making, right? It's like a quick, easy way to think about geometric shapes and their volumetric interrelationships, and you fit them into a hierarchy, very like Kepler did. But you're not modeling, you're not being woo-woo at all here. You can get woo-woo later. You can do as sacred geometry as you want, but this is like, it's not, if sacred gets in your way, push that aside. Just learn the basics here. This is just, and there's a nomenclature that goes with it, right? So the A modules, they fill in terms of completely brick in the unit volume tetrahedron. And since there's 6 times 4, like on the base there, 1, 2, 3, 4, 5, 6, there's like 6 A modules to just fill in a quadrant. If you remember quadrats, those are the 4 quadrats, you could say, here coming off the center of this tetrahedron. You see 4 purple vectors. Think of, just save the word quadrats for later. It's basis of the coordinate system, if you'd like. And then octahedron over here has the additional yellow sliver here, which is, notice, it's just the A module slid up. Keep that length the same. And just push up further. Wait, do we keep that length the same? Yeah, I think so. We'll have to look at the plane nets. I'm asking about, okay, I'm thinking more about the lengths here. So, and the angles, and the fact that there's left and right and so on. So these are the plane nets. Yeah, this over on the right makes these 2 lengths appear identical. You'd think I would know that offhand, but. And then we've got these additional vocabulary. Here we get to the space fillers. Now, if Fuller had been in touch with Somerville, another mathematician, into what tetrahedra fill space, because irregular ones will, like regular ones won't, without assistance from like the octahedron as their complement for filling space. But an irregular tetrahedron, actually, there are several. There's more than, like there's maybe 4 or 5, right? So there's a literature here, and Mathematica can, like the world of math, whatever it's called, Math World. There's all this stuff. It's just we have a slightly, we being in the Synergetics namespace, have Fuller's well-designed, streamlined vocabulary, which those trying to attack him are like, oh, he made up too many words, like neologisms, right? Making up words is considered poor form somehow, but if you look at every scientific jargon on earth, you know, there's millions of words pouring out, new ones. These are pretty cool. Coupler is what's in my hand there. And then might is what we talked about. It's made, is made of a left and a right A and a left or a right B. So you stick the B on either side of this might. Or you'd stick the B on either side of this AA pair of left and right A's. And put a B on either side to get a might, and that's a space filler. Remember A and B right there. I don't know if I really get into the might in these slides. We'll see. I ought to. We're getting into, and then the T and the E modules, we're getting into dimension is what the point of this one is. And that's a rhombic, this tricotahedron, right? Rhombic trichotahedron. That's one of our unit radius balls in the middle. And these will pack in what we call the CCP. It's kind of a home base for Fuller as well. It's sort of a home base in crystallography. It's like there's a lot of lattices, but when you want to sort of find a home base, the thing about the CCP is everything's equidistant to 12 surrounding neighbors. BCC, SCP, they're not really that cool. So to have a unit volume tetrahedron embedded in a CCP is hardly weird. I mean, it's like, that's why the first reaction, instead of curiosity and wow, that's cool, is, oh no, you cannot come into the room with such a possibly disruptive thing. Like, immediately we're protecting the old unit volume, the cube, and it's like it's a defensive reaction, which is not a mathematical reaction, because if you're into math, then you are excited and enjoy like these multiple sandcastles on the beach. You know that axiomatically we're not bolted to one possible and only one possible paradigm, right? Math includes the concepts of multiple maths. It's not a big deal. So you don't have to be reactionary when you see this stuff. Your math, you could say, isn't going anywhere. It's well established. It's here for the ages. It's just, whoa, here's a brand new, interesting set of, you could call them math facts. You see what's going on the very bottom line there. I'm giving a closed form expression in terms of phi. Third root of 2/3 times phi or phi over the second root of 2 equals whatever. And that 0.9994, that's the length of the T module's radius compared to the E modules. And the E module precisely shrink wraps this ball. Like if you crisscross all the facets of the rhombic trichotahedron, those are the surface facets of the 120 E modules. And they each have the volume that they have given this unit radius sphere. Now remember, tetra volumes from here on out. So when I talk about the volume of, it's with reference to the unit volume tetrahedron and the Kepler arrangements, like Kepler-like arrangements. Here's a poster. Like this stuff is very easy and very spelled out and very not a problem and very not taught anywhere by anyone much. Very strange, very strange, very strange, very strange. So this is the difference between an inner and an outer. Like, okay, what if I want the volume? Here's the thing. What if I want the volume not to be unit radius, giving me E modules, but I would like the volume of the whole rhombic trichotahedron to be exactly 5. And we're so little off, as it turns out, even with E modules. It's like that thing's almost 5. I got whole other YouTubes on. This is a big correction between volumes 1 and 2 of Synergetics. It's like Fuller is hot on the trail of his volume 5 and its significance, and finally he comes to it in the form of the T modules, 120 of which make a volume 5 rhombic trichotahedron, but their radius is so close to 1 but not quite. Isn't that interesting? And it turns out we can go places with the T modules. We can go places. We can do the 7.5 volume rhombic trichotahedron, and its vertices now line up with our volume, some of their vertices line up with the volume 6 rhombic dodecahedron, the space-filling one that Kepler likes so much. Another interesting thing, getting into E module territory now, is the volume ratio between the cube octahedron of volume 20. So this is where I get out my jitterbug. And here, back to show and tell. Hold on a sec. Back to show and tell. If you're giving this talk, like I'm encouraging you to just copy me, but do it your way. Use the slides. Let people know this stuff, right? They should be able to. A lot of tuition owed for none of this information at all. So that's like our octahedron of volume 4. We can open it up slowly to where it reaches the icosahedron phase, and then all the way open 20, right? That'll be our volume 20. And this octahedron of volume 4 is the one depicted in this picture. And this icosahedron inside of it is in turn, of course, smaller than volume 4, right? And what we're doing is carving out these 24S modules from the empty space in between. Like these faces here are flush. The icosahedron has opposite parallel faces here, and so does it's like they fit together very, very nicely. Not a new discovery by Bucky, something you'll find going way back, but hey, let's carve up these sort of empty attics, that's like extra roofing provided by the octahedron. Let's kind of use wood framing, and what do we get? What's the shape? And that's going to be the S module. And its ratio, S to E, is the same as the ratio of the cube octahedron, this one, to the icosahedron, 20, 18.51, 20, 18.51. So if you 18 is less than 20, so 20 over 18.51 dot 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 is greater than 1. It's about 1.08 over here on the right or left. We call that the S factor. S to E or VE to I cos. So VE is a synonym for the cube octahedron in this. And once you have the S module going, then look at this, David Koski's research. You can, I'll get to the next slide next. You can take your S modules and scale them up and down by phi or phi. And that's what I'm doing with the two in the jar here that I had printed at the local library before the pandemic. Okay, so these two, let me hold them up. These are phi, this one's phi down from this. In other words, if I multiply all these edges by phi, I'll get the next higher up edges, and I can keep going up and down, phi up and phi down. But when you scale volume, or excuse me, when you scale edges by phi or phi, you're also scaling the volume up or down by phi to the third power. So when we go down a step, call it phi down, we call it lowercase s3, which means we went down phi to the third power. It's like 1 over phi to the third. Whereas if we're just at the regular size, s equals the regular s size. I keep forgetting this isn't a scrollable. This is all on REPL IT, and you can scroll through it and run the Python. And we're showing various identities here between, like, how you can give the whole number volumes, as you see over on the right here. We can express those in terms of so many S modules plus so many S modules phi down plus so many phi up or whatever. See, once you're on the S scale, then you phi up and phi down, and then you figure out the coefficients and a minimum sort of lowest terms way to build in terms of S modules, all these other shapes. And the E modules also get involved. So, and how do we get volume in the first place? Like, it's not clearly the same volume formula. And this is where we could take a couple routes, because there's a fixed ratio or relationship between a synergetics volume for a shape and the corresponding XYZ volume, we could call it. There's a fixed ratio called the synergetics constant, or S3 to the third, S to the third power, could say. But another interesting way to do it, and it's a trivial, trivial in the sense of work, if you've got it automated here in Python, but in any language. In fact, I've taken this formula as an exercise, convert it into new languages that I'm trying to learn, like Rust or Clojure. I've done this in those. And Gerald de Jong came up with this, and he doesn't remember the reasoning exactly. You know, it's one of those math stories, but it works really well. And it's just, you know, there's precedent for this in the literature, where you give the 6 edges, the 6 links of a tetrahedron, and Shazam, you get out the volume based on edge lengths. And this does that, but if you compare it with the historical versions, it's simpler. It doesn't have any big fat constant. I could actually simplify the last line a little, just forget about absolute value. Sorry about that. In any case, you can use this for the volumes, and you have to put in A, B, and C, or pick any corner, any apex of your tetrahedron. Remember, it doesn't have to be regular or anything. Just pick a corner, A, B, and C going off that corner, and then you've got a base opposite that corner. Just call it a base. It doesn't matter where you started. And there you have to do, so you've done A. A is your, O can be your apex, the one you picked, like that's going to be the starting point. And then you have edges A, B, and C, okay, to those corresponding points. You could call them A, B, and C. And then AB is going to be edge D, and then BC is going to be edge E, and then back to the beginning to C back to A is going to be the last edge, right? F. A, B, C, D, E, F. So you just put those edges as a tuple into Python, into this equation, into this formula, and it will come back with the volumes. And that's one way. Another way is just, well, then you'd want the cubic volume. Okay, so if that's how many tetrahedrons would fill this thing, how many cubes, and then with a defined relationship to that tetrahedron. And so we've got that going on also. We can create a class of tetrahedron in Python, use that volume formula internally, and spit out the XYZ volume also. So that's where we get our synergetics constant between these two. So there's a lot going on here with Python. It doesn't have to be in Python. It's just the idea of a computer language fits here. We want you to be coding as part of math. It's like this is a very contemporary curriculum, let's put it that way. There's a jitterbug transformation. It's well known, actually. You can type in YouTube. That jargon has managed to pretty much penetrate into almost mainstream, the jitterbug transformation. See, Fuller got because his detractors had an investment in diminishing his stature, easier to do when he was gone. The idea was he was kind of a hollow man who stole everyone else's ideas, but self-promoted. He was very clever in self-promoting, but really there was nothing really that original about him. He's more of a con man. Now that doesn't hold up to scrutiny at all. I think coming this far into it, I'm giving him all credit here for this kind of stuff. Like, it's easy for me. I don't have to toot my horn about this, which is why I can sound respectful towards Bucky, because that's where I'm getting it. And it's like Arthur Loeb worked with Bucky, and he was a button-down, credentialed crystallographer. And so he got a lot out of this approach to sphere packing, right? Sphere packing is not a new topic, not original with Bucky, but starting from the middle and packing outward in layers and coming up with this formula, 1124292. If you look in the encyclopedia of what is it called? Online Encyclopedia of Integer Sequences. Check the ones out referenced down below, and you'll actually find my name in the links. Because, hey, I've been studying this stuff too. I come out of Princeton, philosophy degree, looking for a career, ending up in computer programming, mostly for nonprofits, but not entirely. And some nonprofits are pretty big, or count the government as a nonprofit. I'd count the whole earth as a nonprofit, because, hey, we're getting the sun as our grant. And we're grant funded. We don't have to pay back. And this idea that all our wealth comes from loans from anybody is just made up. That's how history. So you owe me. We got to establish a debtor relationship. But that all happens in the context of narrative accounting, as I call it. Okay. But the sun ultimately is giving us our steady energy supply day after day. You're not redistributing wealth in an irrigation system. If the water's pouring down from the mountains and you choose to like reapportion a little bit how the water goes, you can call that redistributing wealth, but it's new incoming streaming wealth at all times. And you could say the people downstream were entitled to more of that shared income, right? All I'm saying is the sun is the basis of our UBI. So C60 by Sam Lanahan. I've talked about this in many, many videos. And it's one of the many artifacts we can use show and tell wise. I could jump up and get some C60 within a couple feet of me here. Oh, well, I have the copper one. Copper. C60 makes a lattice. This jack will help you talk about, like, depending on your audience, but you want to talk about how many spokes it has, and we're easing in between 6 and 4 spokes. That's 6 spokes. The jack, octahedron, you could think of that it's inside of, but it's also associated with the octahedron's dual, the cube. So here we're going back and forth between X, Y, Z, and what we could call caltrop coordinates. And this has developed since Bucky's time, a whole spiel, interesting, about caltrop coordinates, or Wikipedia, check it out, quadrate coordinates, like here. And I've integrated it with the unit volume tetrahedron idea, which means the blue vectors aren't actually unit. So do you call them unit vectors? No, you don't have to. You call them basis vectors, though. So and they're 4 basis vectors, 4D space, remember. And, that sounds wrong. And of course, it's just a different sandcastle. It's an axiomatic difference to do the way Bucky does, or the way I'm doing with the quadrays, and I'm not the only one behind these in terms of a pedagogical device. Again, I'm not trying to say we're going to take over the world. The world domination thing is in my heritage, but it had to do with the open source, free open source. That slogan, world domination, that's associated with Linux and the Penguin and all that. And then it became, okay, we've succeeded. Open source rules, right? World domination achieved. There's still a lot of proprietary, and now with cloud native and inner source, and it's gotten to be as secretive as you need it to be, but the tools are pretty open. The main tools, a lot of them. So I'm mourning the loss of this page now, because Math Forum, as of I think as recently as yesterday, is down, and if the past is any guide, is probably down permanently. And a lot of work went into that. Thousands of hours by lots and lots of people. I'm not talking about me. We'll see. We'll see. Maybe NCTM is just belly up now. I don't know. So this is Wikipedia. Hopefully it won't go belly up right away. They have a big endowment, right? So this is how you can add quadrays to get this A through Z. Very convenient, 26 points. Just use the sort of US keyboard alphabet if you want to introduce these vectors. We're talking about vector addition, right, as an operation. Same as usual, but you write it in Python or other language that allows operator overloading, is what I'm suggesting. And you also take advantage of polyhedra being containers and being classes and being subclasses, right? I have a polyhedron superclass, and then each individual polyhedron is its own subclass of polyhedron. All I'm just saying is there's a lot of andragogy and pedagogy already well developed and branching out from here. So after you give this slideshow, if people want a whole week or more, they want to learn more, you've got the material. You're well equipped, right? And you can be quite unique in this market. In other words, almost nobody's teaching this stuff. So I'm saying how, basically like in Git, you can branch. You have 3-4 meanings of 4D is not a problem. It's not that you have to bring them all together and merge them all somehow. That wouldn't work. But they can still talk to each other. It's like you can learn all these languages. As a human being, you're not limited, and you don't have to say, oh, I'm going to commit my life to one of these. Why, right? It's like you can jump in and out of Synergetics, is what I'm saying. There's nothing about it that it's like Martian math. It has a lower gravitational pull, maybe you could say. So I could go on into the Utragon stuff and talk more about the unit volume stuff. And that's what I do in what I call Martian math. And this is more about curriculum design and packaging and the science fiction possibilities. This is called the Tetra Volume, or the Tetra book. And it's conceived of as a book with its flaps open, its front and back covers at 180 on a flat plane, and one page wagging back and forth, tip to tip. It goes in an arc, and it can stop at these various stop points and read out the volume in this case. This was actually running, you'll find these on YouTube. I had them running in Visual Python, I think it was. I've done a lot with Visual Python. These days I'm pushing Blender, which I'm kind of a newbie at. And if we're all sitting on our thumbs waiting for me to make like the Disney versions of all this, or the cartoon I mean, there's so much that could be done here, and that's why I try to make it clear that this is common heritage in terms of how we treat math in the culture. Now that it's published, you've had 40 years to make cartoons and haven't really done anything, and that's interesting. I'm really perplexed in a way to figure it out, but I think we'll have books explaining why, right? Why did we have so many years after the publication of Synergetics that this stuff just sat in a junkyard for most purposes? I don't see any reason for it personally. It's really good philosophy, really interesting, different paradigm at an accessible, right? So it's a geometry of lumps, as I was saying. You don't have to go below 4D in terms of, if you're in volume, everything's a tetrahedron at minimum in a sense, right? It's like everything's a ball or a lump or some kind of piece of clay, you could say, all the way down, right? And that gives us the 4D that we then add frequency to bring it sort of into energetic reality in this language. And we find resonance with Darcy Thompson here. This is from the Huffington Post. He's thinking, what about four-dimensional space in terms of tetrahedron? I don't think Bucky ever knew about this quote. It's quite a find. It's a good job from Susan Mazur. And Geometry of Lumps, Carl Menger, he's got an essay. I've got the citation here that would take us into this kind of 4D lump-like volumetric approach. So I'm saying, once you jump into the swimming pool of Synergetics, you find lots of ladders to climb out in the swimming pool, like a normal swimming pool, back onto already hard ground math, like Carl Menger's established dimension theorist Vienna circle. So you can systematically trace lines from inside Synergetics to surrounding topology or topography, cosmography. In other words, this stuff doesn't exist in a vacuum, of course. And Fuller himself is always throwing out connections to Euler in particular and Gibbs. So he's aware kind of that as he develops his poetic language, Synergetics, that he needs to map himself into sort of civilization, and he does that work. And there was a plan by that Dr. Arthur Loeb I mentioned to get Fuller and Escher together to collaborate to where pictures like this would have been in Synergetics. But here's one beautiful octet truss, or whatever you want to call it, IVM. So we have all our jargon. But the CCP balls I'm talking about, when you pack them together, where these edges meet, those are the centers of those balls, you see. So you get this kind of feeling, which is what Darcy Thompson exactly is saying in this quote. If I were swimming around in this space, why would I say space is three-dimensional? What looks three-dimensional about this? And we're looking at the tetrahedron as the simplest shape, topologically in terms of made of edges, right? Okay, you can say sphere is simpler, but there's a discussion we can have here about the rules, right? If we have to express ourselves in terms of nodes and edges, like segments and vertices, isn't the simplex simpler than the cube, right? And can you have an inside and an outside with fewer coordinates? And with caltrop coordinates, isn't quadrants fewer sectors in space? Like, we're only dividing space into four quadrants here instead of 8 octants. There's kind of an economy here we shouldn't be missing. And people say, well, it's similar to barycentric. Okay, well, cool. How is it? And similar, and let's just do some more chit-chat in the cyber world about all this. And that's why I'm sharing these slides with you, so you can go forth and explain all this stuff, whether I'm around or Bucky's around or anyone. It's all on you now. Okay, so, and you can find all kinds of things you want to be critical about too keep the art world in mind, and this particular book often comes up in these discussions, The Fourth Dimension and Non-Euclidean Geometry in Modern Art by Linda Dalrymple Henderson. That gives a lot of the story, traces us back to P.D. Ouspensky even, to whom Fuller sent a 4D time lock because he recognized Ouspensky as an important author in his day. He lived a long time, Bucky, so, right? Lots of cast of characters come and go, and he's still at it. And, yeah, the tie-in with windmills here is pretty good, because I've been talking about windmills quite a bit. And the grid, and how establishment, doesn't that sound? It's like, this is the question. Is Synergetics too quixotic to ever make it? And my kind of flip, it's kind of an aspect shift. And the Wittgenstein thing is, okay, there's a funny cartoon from XKCD, but is to say windmills are us, or like we are the windmills. It's like this is now, it may not be mainstream in August of 2020, but you can't, now that you've seen this, okay, here's the ending pitch, something like this. You can't deny that this is here to stay, interesting, established, stake in the ground mathematics that is already doing work. Like people are already wrapping their ropes around this stake and pulling it and using it as part of their tent. It's a tent stake, you could say, and it's anchored. So it's not quixotic. It's the opposite, you could say. Okay, you could be quixotic and try to get this to go away, but I don't see any hope for that. And there's the promised picture of Ed Applewhite. Quirky papers, he classified a number of mine and gave them back at his, when he's dividing up his spoils, right? He's sending about half his stuff to Stanford. I don't know exactly, but I just showed up in his Georgetown place about when he was going to get the shipper. And he knew I was coming, and so he wanted to give me the privilege of doing what I want with my papers, some of them. So that's what's on the right there, and that's Jay Baldwin, who I hung out with a very pleasant time, and did some video at that time. And then I've seen him since and before too, but this was our one time when he drove at some distance specifically to talk and see me, so I felt really great. And same with Applewhite, he came out with his wife to see me in Oregon, right? And so that was cool. And let's see, that's it. And then, so going backwards quickly, this is all online. I encourage you, you can give me name credit for the slideshow, but how you talk it through or make your own slides, lots of memes here that you're welcome to. I encourage you to pull from. It's American heritage, right? If in between now and 1980s, when this came out, your college and university have done nothing to update you about this important futurist coming up with this namespace for our mutual benefit. It's esoteric for sure, but it's not beyond the pale, and don't get sucked in by people who confuse it with, I don't know. The thing about Fuller is in Critical Path and all that, he does talk a lot about money and stocks and bonds and financial stuff. So he's kind of scary to the money people. He's critical. He doesn't talk about cryptocurrencies, right? But because this is in the 80s now. But I can see where he's scary to some people, but not to the point, like philosophers have been scary before. And if they've got some interesting math especially, it's like they're going to have to do more work to keep him suppressed than they have. There's been some smearing going on. I saw some stuff in Wired that was pretty lame. There's a lot of lame literature on Bucky, I have to say. Doesn't touch any of this. If it doesn't, open a book on Bucky, flip through it a while, and if none of this is there, yet it was written post its publication, like Synergetics is published, like A Beautiful Molecule doesn't understand, that author, that this is the humanities here. This is a philosophy book. Just he just glanced at this stuff and didn't understand it at all, and then wrote a book in which synergetics is kind of dismissed out of hand. That's very ignorant, but that's also very British, very ethnocentric. So you're forgiven, British person. All right, so lots of fun here. I encourage you to find me online and also look at my other YouTubes. I got a lot, and give you more ideas, especially for weaving in history. Now that we're talking 20th century. All right, talk to you soon.